Welcome to paper 2 for GCSE Chemistry Higher Tier 2023. So for this one, same as the other ones, I'm just going to be breaking down the thought process behind answering the questions and then how to get to the answer. So here we go. First question is about rates of reaction between zinc and sulfuric acid. Hydrogen gas produced in the reaction, shows you the setup, and there's the method. Suggests why the stopper must be put in the conical flask as quickly as possible in step 3. So remember, we are collecting gas from the reaction, going up the tube. So the stopper's there because we're trying to collect all of the gas here. There's no point in waiting 10 minutes and then doing it because it's already lost the surroundings. So all you do for that one is just to stop gas escaping. So this next question, they've calculated the rate of reaction for a trial. Each trial, 4 trials, different rates of reaction. Determine the mean time taken for 20 centimeters cubed of gas. This is a possible 5 marks. Do not include any anomalous results. First off, whenever it says that, it's telling you that there is one, so spot that straight away. Out of those 4, it's that one because that one doesn't fit the rest. So we're going to ignore that in all of our calculations. And we're going to use this equation. Mean rate is volume of gas divided by mean time taken, and we're working out the mean time. So first thing we're going to need to do is work out the mean rate of reaction, which is add them all together, divide by however many there are. So 0.78 plus 0.81 plus 0.81 divided by 3, because we only did 3, we ignored that third one, and we get 0.80 centimeters cubed per second. That is our mean rate of reaction, and we need to work out the time. We're given the volume of gas because it's there. So I'm just going to sub it into that equation to start off with. So mean rate is 0.80 equals volume of gas, which was 20, divided by whatever the time is. So for this one, all we need to do, you can actually, for this kind of equation, you can get away with, you swap those two around how you would arrange it. So our mean time is just going to be 20 divided by 0.80, and we get 25 seconds. The student changed the investigation so the mean time taken to collect the gas was greater. Which 2 changes would increase the mean time taken? So for this, if it's increasing the time taken, it means the gas is being produced not as fast. It means the rate is decreasing. So decreased rate of reaction. Tick any 2 boxes. So ultimately the question is, tick 2 boxes that decrease the rate of reaction. Obviously not catalyst, because that increases it. Using a larger conical flask makes no difference whatsoever. Using a lower temperature, the higher the temperature, the faster the rate, so the lower it is, the slower the rate. Smaller pieces of zinc means it's going to be a larger surface area, so that's going to make it go faster. So it's got to be the lower concentration of acid. Make sure you tick 2 for that one, because it says 2. Hydrogen gas is produced during the reaction. Give the test for hydrogen gas. This is just one of those ones you need to know. We need to know the 4 gas tests. So for hydrogen is you use a lit splint, and it makes a squeaky pop sound. This question is about alcohols and carboxylic acids. Alcohols are fuels. Student burned 1 gram of 6 alcohols. Determine the energy released from each, and there's your results. Calculate the mass of ethanol that must be burned to release the same amount of energy as burning 1 gram of heptanol. So we're talking about ethanol and heptanol, these 2. So the others are completely irrelevant in this question. So ultimately it's asking how many times would that go into that, right? So all you really need to do for that is you just do the heptanol energy divided by the ethanol, and you get 1.34 grams, because you need slightly more ethanol than 1 gram to burn to release the same amount of energy as heptanol, because it releases more per gram. Here we have a relatively easy graph question. So the energy released in kilojoules per gram varies with the number of carbon atoms in 1 molecule of each alcohol. Plot the data on table 2 on figure 2. 2 marks. So we don't need to do the plot, any line of best fit for this. We're just plotting the results. So first off, we figure out the scale. So the first bit, 28 to 30, there are 10 little jumps. So that means each little jump is worth 0.2. And then from 1 to 2, there are 5 little jumps. So on the x-axis, it's also going up in 0.2. So then we go across the corridor, up the stairs. We don't have the alcohol with 1 carbon on it, so we start with ethanol. So we go 2 carbons, and when it was 2 carbons, it released 29.6. So we go along to 2, and then we go to 29.6. So that is there. Make sure you are precise with your plotting, because if you are more than half a square out, you get no mark. 3 carbons along to 3, and then so that's propanol, 33.6. The 4 carbons, butanol to 36.1. So go up to 36, and then go half a square higher. 5 carbons is pentanol, 37.7. You go along to 5, and then up to 37, and then go 3 squares, and then a half. Then you go 6 hexanol along to 6, up to 38.9. So that's going to be half a small square lower than where 39 would be. And then 7 carbons, 39.8. So that's go up to 40, and then go down 1 small square. And then for the next question, estimate the energy released when 1 gram of octanol, which is 8 carbons, is burned. So you imagine you've got like a trend line like that, a bit better than that, but you get the idea. And then you would make an estimate of what the point would be if we had 8 carbons. So on mine it is 40.6. You're allowed a range of answers from that one. Depends on what your line shows. It's 40.4 to 40.8 kilojoules per gram. Carbon dioxide is produced when alcohols are burned. Carbon dioxide is identified by bubbling gas through lime water, which is the gas test. Complete the sentence. So lime water is an aqueous solution of, and then use the name of the compound in the box. The way to remember this, you can either remember it off the top of your head. One way of remembering it is that lime water is alkaline. It's like pH 9 or 10. Which one of those is the alkaline one most, which is calcium hydroxide. Next one, give the results of the test when carbon dioxide is bubbled through lime water. Once again, it's just your gas test that you've got to know. So you bubble carbon dioxide through lime water, it turns from clear to cloudy. So ethanoic acid can be produced from ethanol. What is reacted with ethanol to produce ethanoic acid? In this one, I mean, you know which one it's not. It's not water, because you put ethanol in water, it's just diluted, isn't it? The easy way to remember this is if it's an alcohol group, it's got an OH on the end of it, and if it's an ethanoic acid, if it's a carboxylic acid, it's this one, isn't it? Right? What's the difference? It's gained an oxygen. Which one of those talks about gaining oxygen? An oxidizing agent. Ethanoic acid contains the functional group COOH. Complete the displayed structural formula for this group. 2 ways you could do this. One is you could just know that is what your carboxylic acid functional group looks like, or you could do it from logic based on bonding and structure. Remember that oxygen can only make a possible of 2 bonds because it's in group 6, so it only needs 2 electrons to get a full shell. So that oxygen has already made 1, so it's going to make 1 more to the carbon. And then the other oxygen can make 2, and the carbon, remember, can make 4 because it's in group 4 and it needs 4 more electrons. And you can check it for the number of bonds each one. Ethanoic acid reacts with different compounds. Draw 1 line from each compound, 1 line to a product of the reaction of the compound with ethanoic acid. So we'll do the obvious one first, which is the sodium carbonate formula of sodium carbonate is that Na2CO3. Even if you don't know that, you should hopefully know that sodium is that and the carbonate group is that, even if you don't know the two part, which makes it pretty easy, because out of all of those 5 products, which one is a bit like CO3? It's carbon dioxide. CO2 is formed. And then the other one, ethanol reacting with ethanoic acid. If you react an alcohol with a carboxylic acid, you get an ester. Which one of these is an ester? That's a polymer, it's not that one. That's obviously not an ester. That's an alkene. It's ethyl ethanoate. This question is about chemical analysis. So potassium bromide is used in medicine. A scientist tested a sample of the medicine to show the presence of potassium ions and bromide ions. The sample is soluble in water, which is useful information. Here is the equipment that he has, and we've got to plan a method to test for both potassium ions and bromide ions. You can do this in a bullet point list. One way to do it is to just split this down the middle. So we're going to do a test for potassium ions, we're going to do a test for bromide ions. So to get the potassium ions, easiest way to do that one is your typical testing for a metal using the flame test. So all we need to do is place sample on a clean metal wire. That's just to avoid anything else from causing a change in the flame. We want something that's not really going to react when we start heating it up. And then all we're going to do is heat it with blue flame or roaring flame with a Bunsen burner. And then if potassium forms, if potassium ions are present, think about what flame. You should know what colour the flame goes when we burn different metals. If it's potassium, you get a lilac flame. So that's the potassium ions tested for. Bromide ions, slightly different because it doesn't affect the flame. So what we need to do for that one is, first off, because it's soluble in water, we're going to dissolve sample in distilled water in a test tube. Why distilled water? Because if it's not distilled, it's got other ions in it, mineral water, or the other metal ions present in it, like magnesium and stuff like that. And then we're going to add silver nitrate to the solution, and then if bromide is present, then we would get a cream precipitate observed. Anything else? That's it. Scientists could also use an instrumental method to show the presence of potassium ions in the medicine. Which instrumental method could be used to show the presence of these ions? So this is one of those you've got to think about. If you think about when you're testing for metal ions, usually you're thinking about flame test. The actual instrumental method is called flame emission spectroscopy, which is more accurate because we obviously can only distinguish between certain colours to a certain level of accuracy. However, if you've got spectroscopy, you can literally see the wavelengths, makes it more accurate. So lo and behold, give one advantage using this instrumental method instead. More accurate is one. You can also get the concentration of ions from this method. You can also say it is more sensitive, or you could say less sample needed, because it would be able to detect subtle changes in the wavelengths of light. This question is about greenhouse gases and climate change. Carbon dioxide and methane are greenhouse gases. Which of the following is also a greenhouse gas? One of the things you've just got to know, out of the three, you've got to know you've got carbon dioxide, methane, and water. It's not going to be oxygen because that's in limited supply. That's what we want. We would like more of. Nitrogen doesn't really change. Chlorine is not a greenhouse gas. So in the past 50 years, there's been an increase in world population, concentration of carbon dioxide, concentration of methane, and the mean temperature of the atmosphere on the Earth's surface. Most scientists think this information can be used to explain climate change, explain why the increase in world population may have increased the carbon dioxide. So things that might have increased the CO2 in the atmosphere. So these are kind of common sense ones. So if the population increases, therefore we're going to need the amount of energy that is needed is going to increase. How do we get our energy? It means we're going to have more fuel burned, which combustion produces carbon dioxide into the atmosphere. Another one, we could have, as the population increases, therefore we need more farmland for food. So therefore more deforestation. More deforestation means less trees, less photosynthesis, less carbon dioxide being taken in by the trees, more in the atmosphere. This time it's the same sort of question, but it's asking us to explain how methane has increased. So things that would increase methane. So as the population increases, therefore more food is needed. So therefore more methane made in food production. That's things like your farm, agriculture, loads of cows, etc. You could also put, if there's a bigger population, there is obviously going to be a lot more waste, which makes methane through decomposition. Next one, describe two potential effects on the increase in the mean temperature of the atmosphere at the Earth's surface. This is talking about effects, this is not talking about what causes it. So as the temperature increases, what happens as a result? So you've got things like, these are more common sense, melting ice, therefore rising sea levels. That's 2 marks already, but there's more. Therefore flooding, therefore loss of habitats, and also linking to flooding, more extreme weather. Any two of those will do. The mean temperature of the atmosphere at the Earth's surface has increased. Most scientists think it's caused because of an increase of greenhouse gases. However, some don't give one reason why some don't accept this theory. So the most obvious thing you could just suggest is that there could be other reasons for the temperature change. You could also say it's hard to model, because obviously so many variables over such a long period of time is difficult to create concrete evidence. You could also say that Earth goes through cycles of temperature change anyway. So the argument is whether or not we're even contributing to it, whether or not it's just doing what it would always do anyway. Copper is extracted from metal ores. Chalcopyrite, however you pronounce that, potato, is a metal ore containing a compound with the formula CuFeS2, which reacts with oxygen to produce copper 2 sulfate and iron 2 sulfate. Complete the equation for this reaction. You should balance the equation. You need to make sure that the same number of atoms on each side of the equation. First off, we'll put whatever element goes in the gap. There's only one element that's missing from the left side to the right side in comparison, and that is oxygen. However, oxygen is a diatomic molecule. It exists in twos, which you just need to know. Then we need to balance it. The correct way to do it is to count on the right side. First we've got 4 oxygens in that copper sulfate, and then 4 oxygens in the iron sulfate, which is 8 on that side. How many oxygen molecules would we need? We would need 4. However, you can also do the cheat code for this one if you're really bad at balancing equations. It works most of the time, not always, is look at the number that pops up the most in the equation. That's probably the number that's going to go into the gap in terms of the number of molecules that would be needed. It's not always, but if you've got no idea what's going on with balancing, use that rule and you won't go far wrong. Calculate percentage mass of copper in CuFeS2. There are the relative formula masses. So to do this, of copper, percentage mass of copper, we just do the mass of copper divided by the mass of the whole thing times 100, right? So first off, we're going to work out the mass of this, which is going to be, copper is 63.5, plus iron, 1 iron, which is 56, plus sulfur, but there's 2 of them, so work out the mass of that and you get 183.5. And then, so that's the CuFeS2 mass, and then we're going to do copper's mass divided by the mass of the whole thing times 100, and you get 34.6. Describe a test to show the presence of copper 2 ions in a solution of copper 2 sulfate. Give the result of the test. There's 2 ways you could do it. You could do a flame test, because it's got a metal, it's a metal compound. If you burn copper ions, they will go green, so you get a green flame. That's one way of doing it. The other one is you could also add sodium hydroxide, and if you do that in this one, you would get a blue precipitate. Copper can be extracted from low-grade ores by bioleaching. What is meant by bioleaching? Remember, this one is the one where it's linked to, so there's phytomining and bioleaching. Easy way to remember these is phytomining begins with P, that's the one where you use plants. Bioleaching begins with B, that's the one you use bacteria. So then you just put uses bacteria, wow, and then which produces, I cannot write on this board, leachate solutions. You could also put solutions which contain copper compounds, which we can later extract using displacement or electrolysis, etc. Chromatography question. Figure 3 shows how the students set up the equipment. It even tells you in this that it's about chromatography, so you should already, as soon as you see that word, hopefully be thinking about this setup before you even saw the picture. Student investigated an orange food colouring using 2 different types. The food colouring contained a mixture of red and yellow dyes and was soluble in water. And then this is the method. Student made 2 mistakes when separating the apparatus, setting up the apparatus. Give 2 mistakes the student made. So these ones are pretty obvious for this one. It is soluble in water, so the use of water is fine. However, the water is going above the solvent line. The solvent, sorry, is above the start line. So first thing we can put is water is above the start line. Second, the start line should be in pencil, however it is in ink, so that is our mistake. This one doesn't even ask you, because you sometimes get 4 marks where it says what's the mistake, what's the problem caused, or what are they supposed to have done instead. But for this one you just get 2 marks for spotting the 2 mistakes. Another student set up the apparatus correctly. Here's a table of results. So we're talking about RF values this time. Determine value X in the table. So first off, we need to remember what the RF value equation is, which is RF value is distance that's moved by the solute divided by distance moved by the solvent. Another way of easy way of thinking about this one is it's like a percentage. It's out of the distance that the whole solvent moved, what percentage of that did the solute move? You're basically working out a decimal percentage, really. Retention factor, that's all it is. So we are given in this, we're given the RF value and we are given the distance moved by water, which is the solvent, and we're trying to work out the distance moved by the solute. So first off, I'm going to sub it into that equation in that order before I do any rearranging. Unless you're good at algebra, I'll just put the numbers in first. So the RF value is 0.6 equals, we don't know what the distance by the solvent is, so I'll just write that down. Solute, sorry. And then divide by the distance moved by the solvent, which is 12.0. Then we're going to rearrange that. So we're going to times both sides by 12.0. So we do 0.60 times 12, and we get 7.2 centimeters. Changing the type of chromatography paper resulted in different RF values for the red dye. Explain why the RF value for the red dye is different using two different types of chromatography paper. And we're going to use table 3, which is over here. So the first thing we can say about this is if we look at the two RF values for both dyes, when comparing them to paper A and paper B, the first thing we can say is RF value is less for paper A. So to put that into context, that means the solvent is not moving, the dye is not moving as far up the paper A. Reason for that? So different dyes are attracted to dyes are attracted to different papers, depends on the kind of paper. So we can say the dye is more attracted to paper A. So that's what makes it move up the paper less. So therefore the dye spends more time distributed paper A. Okay, next one. What are the changes? What other change to the investigation could result in a different RF value? So what else could change how far the solute moves up the paper? You could change the type of solvent. So you could say use ethanol. Obviously ethanol would do a much better job at dissolving the dye because it's a better stronger solvent than water is. So you would expect it to move further up the paper. Manganese dioxide catalyzes the decomposition of hydrogen peroxide. Catalyst. Oxygen and water are produced. Explain how manganese dioxide catalyst increases the rate of decomposition of hydrogen peroxide. So this is 2 marks. It's basically asking you, how does a catalyst work? Your first mark would have been it increases the rate, but it's already said that for you. Second thing, by lowers the activation energy. And the third mark that you need to remember in your catalyst explanation is by providing an alternative pathway. Student investigated the rate of this reaction. This is the method used. So explain why the mass of the conical flask and its contents decreases. So remember, when you've got a conical flask, if you had a bung in it, so it was a closed system, then the mass would always stay the same before and after, because the reaction's just rearranging the atoms, but no new atoms are being made. If we are decreasing mass, it means we've lost something. What have we lost? So in this one, it said in the earlier thing that oxygen and water are produced. So the first thing you can say is, well, water's going to stay in the flask, but oxygen is a gas. Yep. So that, therefore, because it's not a closed system, that escapes the flask. into the surroundings, which is why we've lost mass. So here we have a rates calculations question. So figure 4 shows the results for 50 centimeters cubed of 2 mole per decimeter hydrogen peroxide solution with 1 gram of manganese dioxide. The tangent line has been drawn at 75 seconds. Determine the rate of reaction when the time was 75 seconds. So we're going to use that tangent line. It says give your answer to 2 significant figures, which remember you highlight or you circle as soon as you see it, just in case you forget towards the end and miss out on a mark. So the first thing we're going to do is use the tangent line, which they've kindly already drawn for us, and we're going to complete the triangle. You're going to use a ruler for that. Then the first thing we need to do is work out what the scale is, because remember, for the rate, if we want the rate, we're going to have to do the change in the y-axis divided by the change in the x-axis, and that will give us the rate at that specific time, at that specific moment in the reaction. So the first thing, the x-axis, it doesn't really matter because it's on 125 and 25, so our change in x is just 125 take 25, which is 100 seconds. Our total mass lost in grams, however, is a little bit different because we've got a weird scale. So we've got from 1.2 to 1.4, so it's gone up by 0.2, and there's 5 little jumps. So what's a fifth of 0.2? It means each jump is worth 0.04. So we spot what the bits are on the triangle. This one here is 1.76. because it's 1 square down from 1.8, and then this bottom one is 1 square up from 1.2, so that is 1.24. So then if we want to work out the change in y, we're going to do 1.76 take away 1.24, and we get 0.52, and that's grams. Then we work out the rate by doing the change in y divided by the change in x. Change in y was 0.52, divided by the change in x is 100, and you get 0.0052. The answer is in 2 significant figures. I'm assuming that is because you could potentially mess up the tangent, and then you need to still get it to 2 significant figures at the end, even if you do a wrong calculation based on the changes in your y and x. The results for 50 centimeters cubed of 2 mole per decimeter cubed hydrogen peroxide solution and 1 gram of catalyst are shown in figure 5. The student repeated it with 50 centimeters cubed of 1 mole per decimeter cubed hydrogen peroxide and the same amount of catalyst. So catalyst in this is irrelevant. So we're going to sketch the results for the 1 mole per decimeter cubed hydrogen peroxide. Now when we're doing this, we've got the same volume. Now remember, hydrogen peroxide is a reactant in this, and we've actually got the same volume because we're still using 50 centimeters cubed, but we've actually got half the concentration. So that means first off, the rate is going to be less because we actually have a lower concentration of reactants at the start of this reaction. So that means we're going to have a less steep line. Also, because we've got the same volume of solution and half the concentration, we've actually technically got half of the molecules of hydrogen peroxide that we had before. So we're only going to it's only going to be possible to make half of the amount of products that was before. So you will need to end your line at half, which is 0.8, and you need to make sure you curve it so it's less steep than the other one, because we had less concentration at the start, so the rate is slower. So this is a polymer question. Polymer means a chain that is a repeating pattern. It just goes on and on and on. Chloroethene can be used to produce an addition polymer called polychloroethene. And remember, it says ethene, that tells us it's an alkene because it's got a double bond in it. The displayed structural formula is as shown. Draw a circle around the functional group that allows it to produce an addition polymer. So remember, for these alkenes, it is the double bond that becomes a single bond that allows it to repeat the pattern again and again and again. So you just need to circle the double bond in the middle. The bottom one, complete the equation for the production of polychloroethene from chloroethene. So first off, remember it's that the double bond becomes a single bond. So the first thing we can do is we can redraw that structural formula as it is, but with a single bond in the middle instead. Then we need to do something that showcases that it repeats and repeats and repeats. So because it's a single bond, obviously every carbon must make 4 bonds. So we end up with 2 bonds either side of that. And then to show it can repeat as many times as it wants to, we just need to put an N outside of the brackets. Polyethylene can be strengthened with wood particles to make some building material, which consists of wood particle reinforcement embedded in a polyethylene matrix. What general name is given to materials like this? So when we put different material into something that's not necessarily an alloy to strengthen the material, the name of this is a composite. And then the amino acid beta-alanine is a formula as follows. Beta-alanine polymerizes to produce polypeptide in a small molecule. Name the small molecule produced when beta-alanine polymerizes. Now for this one, you just need to look at the ends of it. So we've got at that end there's hydrogens and at that end there's that. Obviously something's going to go away so we can repeat the chain again and again, and something's going to have to come off this end, something's going to have to come off this end. What can you think of that you can make from hydrogens and water and oxygen to water? An amino acid can be represented as follows. The relative formula of this amino acid is 75. Calculate the relative formula mass of the section in the middle represented by. So you want to figure out what is the mass of this bit in the middle. Easily done, it's just easy maths. So you just got to work out what's the mass of that, what's the mass of that. Obviously the whole thing is 75, so take it away from 75 and you'll get whatever the unknown thing is. So let's work it out. So for the COOH and then the H2N. So H2N, it's going to be 2 for hydrogens plus 14, that's 16. And then for the COOH, we've got 12 for carbon plus 16 plus 16 plus 1. So 32, 44, 45, 55, 61. And then all we're going to do is, the whole thing was 75, so we're just going to do 75, take away 61, and we get 14. Figure 6 represents part of a naturally occurring polymer molecule produced from glucose. Draw a circle around the repeating unit in the polymer in figure 6. So you just have to look at it and spot the pattern. Obviously there's 3 repeats there. Can you circle 1 repeat? Done. Then we look at suggesting the identity of the polymer. So you should hopefully know at this point the glucose is broken down in the body mainly from foods that we have. It's carbohydrates that's broken down from, and that is specifically called starch. You could also have cellulose, because cellulose is a built up polymer structure of glucose. You could have glycogen. You could also have polysaccharides. Any of those will do. Figure 7 represents the structure of a naturally occurring polymer. Everybody all the way from year 7 to 11 and beyond should be able to look at that and say immediately that this is DNA. Give the general name for the 4 different monomers which make up the structure shown in figure 7. So for this one you just need to remember that they are known as nucleotides. Name the shape of the structure shown. So what do we call this specific shape? it is a double helix. So this question is about reversible reactions. When 4.68 grams of hydrated copper sulfate is changed into anhydrous copper sulfate, 2.99 grams of anhydrous copper sulfate is produced. And then we've got an amount of energy taken in surroundings. It's endothermic, doesn't matter, it's irrelevant for this question. For this, we are working out the maximum mass of water that can be made if we use 11.7 grams of hydrated copper sulfate. So, first thing you need to think about for this question is conservation of mass. What comes in must come out. So, if we react 4.68 grams of copper sulfate hydrated, we're going to make that much copper anhydrous copper sulfate and a certain amount of water. It's got to add up to 4.68 because it's conservation of mass. What goes in comes out. So if we react that together, we will get 1.69 grams of water. The way I would do this is I would work out, well, what percentage of the products end up as copper sulfate anhydrous and what percentage end up as water. You only need to work out the water percentage. So the way you would do that is you would go 1.69 divided by 4.68 gives us 0.361, which is, you could times by 100, it's technically 36.1%. Then we've got what amount of water, what mass of water we were going to get if we react 11.7 grams of hydrated copper sulfate. Well, 36.1% of that is going to become water. So we just need to figure out what's 36.1% of 11.7 grams. So we just go 11.7 times 0.361 and we get 4.224, or we can round it to 4.2. Done. So for this question, 15 grams of anhydrous copper sulfate completely changes into hydrated copper sulfate when water is added. So we're actually talking about the reverse, the other way around now. Calculate the amount of energy transferred to the surroundings. So remember in this one, when we did 2.99 grams of anhydrous copper sulfate made, using this much, but this number doesn't really matter right now. When we made 2.99 grams of it, it absorbed 1.47 kilojoules. Now the question is how much energy is going to be, obviously, if that energy would be released, if 2.99 grams of anhydrous copper sulfate water was added, it would be the same the other way. However, we're trying to figure out how much energy would be released if we used this much anhydrous copper sulfate. So all we need to figure out is how many times bigger is this than 2.99, and then figure out that's what we need to do to our energy number. So first thing we need to do is 15.0 divided by 2.99 and we get about 5.0167. You could just put the answer button on your calculator and then you're just going to times that number by 1.47. And you get 7.37 kilojoules. The gases nitrogen dioxide and dinitrogen tetroxide reach dynamic equilibrium in a sealed container. The equation for the reaction is as follows. The forward reaction is exothermic, so exothermic, therefore the backwards reaction must be endothermic. So what happens to the position of the equilibrium in this reaction if the temperature is increased? Now what you've got to think about with this is equilibrium reactions, the way to imagine it is it's like an angry teenager, much like you lot. So you need to think about whatever you do to the reaction, it will do the exact opposite to reach equilibrium again. So if we think about if we're increasing the temperature, that is favouring the forward reaction because it's an exothermic reaction which increases in temperature, releases energy. So therefore the reaction will do exactly the opposite. It will shift the equilibrium in the other way. It will move to the left. The teacher pushes the syringe piston in. This increases the pressure in the gas syringe. What is the colour of the mixture when the new equilibrium position is reached? So for this one, we're talking about pressure. We're talking about the number of molecules. So we're not bothered about exo-endothermic anymore. We're bothered about how many molecules there are. For this one, this side has got more molecules than this side. So if we increase the pressure, that favours, remember it's always going to try and do the exact opposite, so that favours this side. So therefore the equilibrium is going to try and do the opposite, and it's going to move to the other side, so it's going to move to the right. Then we need to look at the colours of the substances. So the thing on the left is brown, the thing on the right is colourless. So it's going to go more towards colourless than it is towards brown. It's going to go away from brown towards colourless. So we look at the 3 boxes we could possibly tick. It's not going to be the same shade of brown because that just implies that nothing's changing. If it was to go a darker shade of brown, that's implying that the equilibrium is going to the left. That means that it's producing more nitrogen dioxide, but it's not. It's going the other way. So there's less brown, more colourless. It's going to be a lighter shade of brown. Hydrogen iodide gas decomposes into hydrogen gas and iodine gas at high temperatures. The equation for the reaction is as follows. Here's another equilibrium reaction. Explain the effect of increasing the pressure on the dynamic equilibrium position of this. So we're talking about pressure, we're talking about number of moles, number of molecules. So we decide first off which side has got more molecules or less, etc. So this side has got 2 moles because of the 2, and this side has got 2 moles as well, 1 of each. So there is actually the same number of moles on this one. So if we increase the pressure of this, it doesn't actually favour either side because there's the same number of moles on each side. So for this one, if we increase the pressure, it has no effect on the equilibrium position. That's because we've got the same number of moles on each side. Suggest the effect of adding a catalyst on the equilibrium position of this reaction. Has no effect on equilibrium whatsoever because it's all about increasing the rate of reaction. It's nothing to do with equilibrium, so it has no effect. Copper forms coloured compounds. Hydrochloric acid is added to an aqueous solution of copper compound A. The word equation for the reaction is the reaction mixture is green when both copper compounds are present in a solution because it's blue and yellow together making the green colour for each copper compound mixed. How can the equilibrium position be shifted to make the reaction mixture more yellow? So we add more acid, more water, or leave the reaction for 30 minutes. This is going to have no effect because it's just going back and forth at the same rate. That's just a complete waste of time. The other two we need to decide. So if we look at, for this one, we're looking at kind of moles on each side, how much of something is on each side. If we add more water, that means there's going to be more moles of it on that side. Remember what we said before about equilibrium going the opposite way? That would mean that if we had more water, the equilibrium would go left, so then it would start going more towards blue. If we have more hydrochloric acid, that means it favours the left side because there's more moles on that side. So therefore, it's going to push it the other direction, it's going to push it to the right. So that means it would make more of the yellow stuff, so it's add more acid. The concentrations of the substances in this reaction do not change at dynamic equilibrium. So that means at the equilibrium point, it's all about reversible reactions. It's at equilibrium because the forward reaction is the same as rate as the reverse reaction. So that's literally your answer. Easy enough. This question is about fertilizers. Compounds of nitrogen, phosphorus and potassium are used as fertilizers to improve agricultural productivity. The table shows an information about 3 compounds A, B and C that can be used as fertilizers, and then shows us a bunch of information about 3 compounds. Scientists analysed the percentage of each of the elements in soil. Percentages of nitrogen and potassium in the soil were lower than percentages needed for high agricultural productivity. There was sufficient phosphorus in the soil, which means it's not needed. Therefore not needed as much, whereas for this one we need nitrogen and we need potassium. Evaluate the use of components in table 4 to improve agricultural productivity of this soil. So we're just, first off, we're doing an evaluation, we need to make a final judgment overall, make some judgment statements at the end. But to do that, we're going to have to pull apart the information that relates to what information they've just told us in the question. So we need potassium, we need nitrogen, we don't really need phosphorus. So first off, you can say compound A contains potassium. I'll just put the symbols for this to save space. Only contains potassium only, and it is the only source of potassium, so is needed. Okay, B only has nitrogen, so, and it also contains more nitrogen than in compound C. We can also say about that one, so it's therefore it's preferable over compound C. We can also say about that one that contains more nitrogen is cheaper. And then for compound C, has phosphorus, which is not needed, as mentioned in the question. So overall, to make a judgment, no compound has both nitrogen and potassium, so we need a mixture. Ideally you want A and B should be used because they've got both. You could use A and C because it's got both in, but you would choose, you can even write further, you would choose A and B because B's got more nitrogen in it than C, and C's got an irrelevant substance in it. How is potassium chloride obtained from Earth? Just like you would obtain any other ore, mining or quarrying from the ground. Name one other compound that could be used instead of potassium chloride to give a similar improvement in agricultural productivity. Just give another similar compound to that one. Potassium sulfate is pretty similar. It's going to react and it's going to do pretty much the same thing. Nitric acid is needed to produce ammonium nitrate. Compound B, name a compound needed to produce nitric acid. Ammonia. It's got nitrogen and hydrogen in it. Phosphate rock contains phosphorus compounds. Plants absorb phosphorus compounds dissolved in rainwater. Suggests why phosphate rock cannot be used directly as fertilizer. It's kind of a clue in this, so it's not soluble. So therefore can't be absorbed. Next one. Phosphate rock can be treated with different acids to produce salts useful as fertilizers. Name the salts which are produced by treating phosphate rock with sulfuric acid and phosphoric acid. You got to think about rock as well as always. It's always got calcium carbonate in it and stuff, etc. as well. So for sulfuric acid, we could end up with calcium sulfate. You could also end up with a single superphosphate. And then for phosphoric acid, we could get calcium phosphate, same rule as before, or we could end up with a triple superphosphate. The first answers for each one is more obvious than the second.